Now, question 3. A hollow ball has a mass of 0.310 kilograms and radius of 0.340 meters. Okay. The ball is thrown vertically upwards from rest. It rises through a height of 1.40 meters. See, that's shown in the diagram. Then drops down again. When it is released, it is moving upwards at 5.24 meters per second. So that is its vertically upward velocity. Look at that. And rotating at 2.70 revolutions per second. So that is its angular velocity, 2.0 revolutions per second. And this is its linear speed, which is 5.24 meters per second. That's linear speed. That's angular speed or angular velocity. During the throwing action, a tangential force of 0.480 newtons is applied to the surface of the ball for a period of a quarter second. Show that the angular speed of the ball when it is released is 17 radians per second. Let's begin by that one there. We know it was at rest. It said the ball is thrown vertically upwards from rest. It wasn't rotating and it wasn't having translational velocity. So the omega initial angular velocity is 0. The final angular velocity is 2.70 revolutions per second. And I can write it like this. Omega initial angular velocity is equal to 0. Now, the relationship between angular velocity and frequency is that omega is equal to 2 pi f. Not a complicated reason to remember that. Understand simple geometry. One revolution is 2 pi radians, right? Pi radians is 180 degrees. One revolution is 360 degrees. So one revolution is 2 pi in terms of radians. So if it's f revolutions in a second, how many radians in a second? Each revolution is worth 2 pi. So f revolutions in a second means 2 pi f radians per second. So our final angular velocity, omega final, will be 2.70 revolutions per second. So that will be 2.70 times 2 pi times 2 pi radians per second. Okay. Now, always think of your linear equations and you can then get the corresponding angular equation. Angular, they just wanted the angular. I've started working on the next part by mistake rather than just this one. This is the angular speed they wanted. So what is our final angular speed going to be? Omega final will be, when you multiply this out, 2 pi times 2.7. Gives us 16.96 or basically 17 radians per second. Right. So that's the answer to part A, just converting the frequency of revolution into radians per second with the 2 pi. Part B. Show that the angular acceleration of the ball before it is released is 67.9 radians per second squared. So during this process, we want to calculate angular acceleration. Think of the equation for linear acceleration. That will be delta V on delta t, isn't it? Just good old linear acceleration. That's V minus u on delta t. Now put that in its corresponding rotational terms. Angular acceleration, average angular acceleration. And we give that the symbol alpha, is going to be the change in angular velocity, delta omega rather than delta v, on delta t. So that's going to be omega final minus omega initial on delta t. And just put everything in its correct SI unit. Now looking at this here, our omega initial was 0 and omega final was 17.6 radians per second. So our delta omega is going to be 17.0 divided by the time interval, which we were told all this happened in 0.250 seconds. So we divide it by that 0.250, and that gives us 4 times 1760. The reason being, we use 17.0 here. If on the other hand, we had actually kept our 2 pi times 2.7, you would have got this 67.9. Otherwise, we get 68 with this. Okay. But if you kept it correctly, that will give you, it's approximately 68 radians per second. But if you didn't round it off, you would have got this number here. Oh, not radians per second squared, of course, because it's angular acceleration. So if you put 2.7 times 2 pi and divide it by 0.25, you get that one there. Calculate the rotational inertia of the ball. Now, when you know the angular acceleration, we also know the force that's applied and the radius. Tangential force of 0.480 newtons, and they gave you the radius of the ball. Make sure everything's in SI units. Here we are. I'll work that out in a different color. Radius of the ball. And if you apply a force tangentially of, where was that force now? 0.480 newtons applied to the surface. So it's a tangential force, right? So I can get the torque. Torque is R times F, the distance, which is the radius here times the force. And that radius, we were told, was 0.0340 meters, 0.0340 meters, times that force was 0.480. Now, just like we have the equation F equals MA, M will be F divided by A, we can write that our moment of inertia I will be, the corresponding thing to force is the torque, divided by the angular acceleration alpha. Right? These are all equations you know. Torque is I alpha. So I'm just rearranging it to I is equal to torque divided by alpha. And then that will give us the torque, which is this number here, 0.0340 times 0.480 divided by the value of alpha, the angular acceleration, which we know from the preceding part was 67.9 radians per second squared. So if I put that there, 67.9, and do the division, that gives us the moment of inertia as being 2.40 times 10 to the minus 4, and the units of moment of inertia are kilogram meters squared. I'll just put a line there so we don't cause too much confusion. So that's the answer you work out to part C of that. I'm using I equals tau on alpha in the same way as we use M is equal to F over A. For the following two situations, ignore air resistance and explain if the height to which the ball rises will be less than, greater than, or the same as 1.40. The ball is not rotating, but is given the same linear speed when it is released. Here the height will be the same. The reason being, the height is determined by the linear velocity. That's the one that's pointing upwards there. The rotational velocity only affects how fast the object rotates, not how high it travels. They are two separate things. Okay? So that doesn't matter at all. Same linear speed when it is released. If the linear speed is the same, it goes to the same height. 2. The ball is solid instead of hollow, but has the same mass and radius. Now, if the ball is solid, some of the mass of the solid ball is closer to the axis of rotation. So the solid ball has a smaller moment of inertia. I is smaller for the solid ball. Because with the hollow shell, all the mass is distributed at the periphery, so it is further away. But with a solid ball, the mass is all the way from the center to there, and the total mass is the same. So the I is smaller for the solid ball. Okay. If the ball is solid instead of hollow, but has the same mass and radius, the same amount of total work is done. So you do the same amount of total work to give the ball its linear and rotational motion. And it has the same angular speed. Now, if it has the same angular speed, tell me what will happen to its kinetic energy, the rotational kinetic energy. The rotational kinetic energy is half I, which is the moment of inertia, omega squared. Now, the same total amount of work is done to give the ball its linear and rotational motion, and it has the same angular speed. If it has the same angular speed and I is smaller, what does it say about the kinetic energy of rotation? I is smaller and it has the same angular speed. So the rotational kinetic energy is smaller. So because of this factor, right, and because of that equation, I is smaller, omega is the same, because don't forget it said same angular speed. There we are. AE rotational will be smaller I, same omega, smaller. So if the rotational is smaller, look at what it also said in this question. The same amount of total work is done. So the same amount of total work means the total energy is the same. Same amount of total work is done. So the total energy is the same, but the rotational part of it is smaller. Therefore, translational kinetic energy is bigger. So I can say, therefore, because this rotational part is smaller and we did the same amount of total work, I can say translational kinetic energy is larger. And then you know what's going to happen to the height. If the translational kinetic energy is larger, the linear speed is larger. Therefore, what can you tell me about the height to which it goes? Height will be greater. It rises to a greater height because it has got greater translational kinetic energy, which means it will have a greater increase in gravitational potential energy. It is capable of having a greater increase in gravitational potential energy, so it will travel higher. Thank you very much for attending the session today, and I hope you found that beneficial, and I would really very much appreciate from your My Courses page if you can please complete the feedback form, because we'd like to know what you thought about the program or the lesson today, and any suggestions for improvement or any other ideas, and also about the online course format. We would really like to hear that. Thank you very much for coming, and it has been a pleasure, and I hope you learned something through that.